Hi, and welcome to our next session here in our chapter on feature selection techniques. He'll talk about wrapper methods. So wrapper methods are due to Ron Harvey, now more than like 20 years old. I guess they are not that hard to understand. So we're basically mapping the feature selection problem to a discrete optimization problem in a binary search space, so whether we're going to include a feature or not. Yeah, we'll discuss the basic algorithmic principles and basic algorithmic variants, so forward and backward search. Talk a little bit about that we can also use evolutionary algorithms for feature selection with wrapper techniques, although I'm not going to spend too much time on that because this is not like a dedicated lecture here on optimization techniques. We'll and also discuss some of the advantages and disadvantages, I guess, hopefully as always. So wrapper techniques emerge from this idea that probably different sets of features can be optimal for different learners, depending on whether you use something that's linear, something that's non-linear, something that's, I don't know, more like smooth, something that's more like tree-based. Maybe different feature sets can be optimal for different learners. Actually, yeah, well, I didn't show that directly, but we also have seen a couple of examples in some of the previous sessions, which at least might have indicated that. And what we're now going to do is that we are also asking ourselves, wouldn't it be great if instead of doing some like approximate stuff like filter techniques and so on, which measure something that could be useful, but they're not like measuring the real thing that we're interested in. And I guess the real thing that we're interested in is how good is a model going to perform in terms of its predictive performance under a certain performance metric with respect to a certain feature set. Wouldn't it be great if we would measure exactly that to guide our optimization? And wrapper techniques now will do exactly that. So we will usually talk about sets of features. S here, my pen tool is as always not working. So this S here is just going to be some feature set under consideration, and we'll now create an objective function just for that feature set, and the objective function might actually just be like use the features, train a model with respect to these features in the set, and then evaluate them on a validation set, or maybe cross-validate your learning algorithm with respect to this feature set, and then come up with a search strategy so you move through that space of potential feature subsets efficiently. So what I will usually talk about here are variants of these wrapper techniques where we really evaluate the model on some validation set with respect to the performance metric that we're interested in. And definite advantage of wrapper techniques is that they really, I guess, optimize what you are interested in. And because we're going to use black box optimization techniques, we're not like going to exploit a lot of the internal structure of our ML model. We can really do that. So if we have like some weird performance metric, there's nothing holding us back using that. I guess we could also kind of discuss things based on maximum likelihood, things based on the linear model, where then we might use not really test error, but something like ARC or BRC as a criterion. I'm not going to discuss that too often. I guess I might have one or two examples in here because they're a bit faster to produce. And the search strategy behind that is very similar. Now, how is our search space now going to look like? You can either say, well, I have my features here, I don't know, let's maybe give them some numbers, so 1, 2, 3, 4, and 5. Maybe I'm working, I don't know, on the iris data set, and these would be all of my features. So 4 is not a super large number, but it's easy for me to work with that on a slide here. And I can now create subsets. So for example, I can say, maybe I'm using just feature 1 and 4, and that would be a subset, and that would give rise to a certain performance value. And I can take a look at maybe at that set here, maybe at this one here, and that would give rise to different performance value. And this subset here, that would be a way of representing my feature subsets. I guess so far, so I don't know, so boring. Another way of representing these subsets is through binary vectors. Guess we could also call them something like characteristic functions. So we would have a binary vector which is as long as as many features we have. So for like for each position here, we'd have like a bit, a boolean, which tells us whether we are going to include that feature or not. So if I wanted to represent this set here with 1, 4, I would say, well, that feature is in, and that feature is also in, and these two are not in. So I'll do a 1, 0, 0, 1 vector. And I could now take a look at the left-hand side here at this diagram, which writes down or enumerates, visualizes all of these 16 possibilities that I would have for subsets, because if you look at the power set of this feature set here going from 1 to 4, that will have 2 to the power of 4 elements, which is 16, right? So 2 times 2 times 2 times 2 elements, because for every bit I have 2 choices. And this guy here, we can now identify somewhere on the left-hand side, probably in this row here, I guess. I'm not very fast of seeing it, but I guess it's here. Yeah, here it is. Now, I've now visualized this here in this diagram in a certain way. So on the first level, you can see the empty set, so with 0 included features. Here you can see on the second level, you see all of the subsets with exactly 1 feature, then 2, then 3. Well, no, that's not a 3, that's a 4. Apologies. Let's remove it. So here we have 3 features, and I guess there's only 1 set with 4 features. And what do the edges symbolize? Well, there's an edge between 2 sets. If there's exactly a Hamming distance of 1 between the 2 nodes, and a Hamming distance of 1 means 1 bit is different. In this special representation here, if we order this also by size, this will also represent the subset relationship, right? So if a feature, let me actually remove stuff again. So if we have a set here, and this set is below another set, and there's a path to that other set further up the graph, then this first one here is going to be a subset of that second one. And you can also see, if you now follow this path, which features actually get added in to like kind of go from the subset to the parent set. And exactly these types of operations we will perform when, or we will likely perform if we now run search algorithms on this search space. And I guess let's do that. So yeah, some formal stuff before, just to kind of define the notation. So like I said, I'll usually now represent my features just as some numbers from 1 to p. And S is going to be my feature subset under consideration. And I will now just define an objective function here, which maps from this set here of all of the features, so from this power set of over S to some real value, and this real value is going to represent the performance of my model if I just use feature set S in my model. And we have also already discussed the relevant choices for that. So either this is going to be something like my validation error, cross-validation error under a certain performance metric, or it's going to be some in-sample error like training error or ARC or BOSC. But if we're using really nonlinear, non-parametric models, as we are in machine learning normally, then I guess it's a pretty bad idea to optimize this training error, so we'll overfit very, very quickly. So these likelihood things, they are usually only looked at, and even there, they are a little bit frowned upon for linear models, and I don't want to get into that discussion now. But first of all, we can overfit pretty quickly by doing that, potentially even for a linear model. But what might be worse is that if we would be running a linear model, then usually we're more interested in inference and maybe, I don't know, confidence intervals on our parameters and so on. And this is not so naively easily possible if we run these forward searches, yeah, and we'll get biases in our p-values. But like I said, I don't want to go into this here. So we are mainly going to assume that there's some nonlinear ML model that we're going to use, and then it's rather cross-validated error. Problems can occur here as well. So if we're interested in generalization performance and so on, we have to embed all of this again in nested resampling. Maybe let's discuss this at the end. At the moment here, I want to mainly discuss now how the search algorithm works and how the search algorithms work, how they operate on that binary search space. And I also want to take a few minutes to discuss how hard the problem actually is. So I guess first of all, we could talk about the size of that search space. So I guess we did that already on the last slide when we looked at the element, the set with 4 elements, and we said, well, the power set has 16 elements, so it has 2 to the p elements, right? So it's exponential in p. So even if p just has some medium value, I don't know, of 100, 2 to 100 is a fairly large number. Now, although this power set, so this size here of our complete search space might be super large, that would not necessarily mean that we have to search this space whose size is exponential in p completely and exhaustively, right? So nobody is saying that yet, but I'm going to say it kind of now. So the problem is that we can actually show that even if we would use a very, very, very simple linear model, and we wanted to optimize just, I think, training error perfectly for that. So that's kind of the simplest scenario you could come up with. That problem can be characterized as being NP hard. So, and of course, formally, this does not imply that there can only be which is like exponentially expensive in p, but it's very likely that this is true. And this probably means that if we would like to solve that problem perfectly, we'll have to wait for a very long time, or we could be okay with using heuristics. On the other hand, in ML, there's usually this kind of, there's this problem if we kind of too aggressively optimize things, we might actually overfit, or here I guess we could call, I don't know, meta overfit or something like that, or over search. So it might actually be interesting to use algorithms which are not perfectly optimizing the search space, but which are a little bit simpler, which are maybe a little bit more greedy. This might actually give us also kind of a regularization component in the search, and on the other hand, this will be less expensive, and exactly that is going to happen if we look at things like forward and backward search, so they don't scale exponentially in p. Yeah, okay, so maybe it's time now to take a look at our first algorithm here. So I'll now introduce greedy forward search. So we have our feature set here. I guess we are now going to run it not on Iris, but we are running it on the bike sharing data set. And we are again using 4 features because we're just, I guess, restricting the features to be just wind speed, temperature, humidity, the feeling temperature. I guess that's what you feel that the temperature is. I can tell you the real temperature here in Munich is quite hot. I think close to 30 degrees, but it feels like 40 degrees. Yeah, it's not so nice to record videos today. Yesterday was even worse. Now, this is a regression data set, so actually, I guess we're not really running a classifier here, but we are running a regression model. I'm not exactly sure what we're doing, whether this is like a linear model or in random forest. Doesn't really matter, and we'll evaluate that with root mean square error. So how does the algorithm now work? Well, the first thing we could do, or we kind of have to do, I guess, is we evaluate our first feature set, which is the empty set. So basically train a featureless learner, so something that just like, doesn't access any useful information. It can take a peek at the distribution of the y values, and we can now use a constant value. So for the RMSE, the best constant is going to be the mean, or maybe we spit out some random values from the histogram of y, whatever. In any case, this is going to give us pretty bad value for the RMSE, and you can see that here. And the next thing we are going to do is we are going to evaluate now multiple models which include exactly one feature. So we'll use our model together with just the wind speed feature or with just the temperature feature. And we'll now evaluate that on a validation data set or through cross-validation. And for each of these one feature sets, we get one RMSE validation score. And then we'll just take the best one. And I guess the best one is always marked in red here. So that's the feeling temperature. So I guess whether I'm inclined to rent a bike or not is quite dependent on how hot I think it is. And I guess, yeah, judging from today here, I find that quite plausible. So what we now do is that we take that feature here into our set, and forward search is called greedy forward search, or it's called a greedy algorithm, because this adding in, this inclusion of felt temperature is never in the future going to be changed again, right? So we are going to remove the feature anymore. It will now stay in the set. The only operation we can do is add in more features. There are variants of greedy forward search which are sometimes called floating search and so on, where you can actually do backward steps and remove the stuff. But in the most basic algorithm, we just add stuff in and then at some point we stop. So we now have this feature in. So now there are just 3 features left, so p-1, to try out for further addition into the set. So now we add that feature in. I guess that's the, hang on, well, that's actually a little bit weird. So is there, I think there might be I think there's like maybe a mistake in the plot here. I guess that's not felt wind speed, but really wind speed. Why does it always say feel here? I think that might be a mistake. So we can now take a look at wind speed, temperature, and humidity and add these in tentatively into our feature set. So we now have this guy and this guy, or we have this guy and this guy, or this guy and this guy, right? So conditional on felt temperature being in there. Oh my God, I'm a total idiot. I don't even understand my own slides. Obviously, this here means that felt temperature is in the set. So this is not a plotting mistake. It's actually, that just means it's in there. I was just confused because it just says feel and not felt temperature. So obviously this is now the 2-element set with felt temperature and wind speed. And here we have felt temperature and real temperature, which is especially confusing because it now says feel temperature. Anyway, and again, we will just pick the best of these 3, which is this guy here, which again you can see from this arrow being red. Now there are only 2 choices left, just because we are using a very, very smallish, toyish example here. So now we evaluate 3 feature sets because feel, felt temperature, and humidity are already in there. Now there's only the choice to add in wind speed or real temperature. Again, we will take the best of the 2. So this is this guy here, and then, well, there's just one thing left to evaluate. Now, how do we terminate? When do we actually stop? So we would usually stop this algorithm either if the performance does not improve any further, or we have reached the maximum number of features that we would allow ourselves to consider. So usually we might combine the 2, or and especially for performance, we would probably say something like, I want to see at least like an increase of, I don't know, predictive performance of at least this, because you probably also, you might quite often be in situations where you want to early stop this thing to create a set of features which is quite small, which is quite sparse. There's also greedy backward search. So works pretty similarly. So we now start with the full set of features, and now we generate all feature sets where we have removed exactly one feature. Cross-validate that, evaluate that, pick the best one. So best one here would be the one where, what can now happen is that if we remove a feature, performance could actually increase because using less features, as we have discussed before, might actually be better, or performance doesn't go down a lot. In any case, we would, from these P choices, we would again pick the best one, and then again remove a feature. Tentatively, we would remove every feature that's in the set, and then again take the best one, take the best one, take the best one, or remove the one that doesn't hurt, that hurts us the least, and do it again, do it again, do it again. Do we have a plot here? Yeah, we do. So here we would start with the 4-element set, go down this path. So here we would have removed, let me see, I guess we have removed felt temperature here. Here then we have removed wind speed, and at that point we also might stop now. So here I guess we might use a slightly different stopping criterion, because we don't always would assume or require that performance really goes down by us removing features that might be a little bit too optimistic. That might happen, but we might not really require that it happens in every step. I guess what we would usually say is that for the optimal current choice, we would like performance to either improve or not go down by too much. So I guess we would allow our performance to go down a bit by achieving a smaller and sparser feature set in the end. Okay? I guess what we could do now is we could compare the two a little bit in terms of how expensive are they. So how do they scale in P? Hopefully this is not too difficult to figure out, so maybe we can actually do that. Yeah, I guess we could do that from this guy here, or from this guy. So how many feature sets are we trying out in each iteration? So I guess that's one. That's not too interesting. So first iteration, we try out one feature set in forward search. Then we have P features to try out. Then we have P-1 features to try out. Then we have P-2 features to try out. I guess you are seeing where that ends up with. And then at the end, it's one again. So what this actually comes down to is that we are summing up J equals 1 to P J, right? And what is that? Well, that's going to be P over 2, right? So that's P times P-1 divided by 2. So that's roughly O of P squared, right? Which you can't see because it's behind my head. And this is what happens in the worst case. If you have to kind of, if you would not stop early on, if we would go down the complete graph, and what happens for greedy backward search? Well, the same, right? So I guess we just, yeah, it's pretty much the same, right? So again, we try out one thing in the beginning, and then P, and then P-1, P-2, until we end up just trying out one thing, which at the end then would be the empty feature set. So they are roughly going to be of the same speed. On the other hand, we could also think a little bit about, actually, maybe I should go to the slide that I wanted to go, which is this one here. So we could also think a little bit about, are they really kind of the same speed? Is there really no difference? Well, there is one, and that is if you also have to think about how much you have to invest to train your ML model. And if you run forward search, well, your first model is going to use the empty set, so you don't have to train your model a lot. And then you're training models with one feature, and then you're training models with 2 features, and then you're training models with 3 features. And your model is likely going to scale at least linearly in P, maybe even more. So if you compare this now, what happens with backward search, where you train on all of the features, and then you train on P-1 features, and then you train on P-2 features, the model training in forward search is going to be much, much cheaper than in backward search. So for that reason, forward search is usually cheaper. It will also usually result in smaller feature sets, because you kind of, if you early stop and you kind of start from the empty set, well, you kind of like having a preference, yeah, for your selected feature set being closer to the empty set. Backward search usually is more costly because of the reasons I just explained. It usually creates larger feature sets, as a result, but usually because it starts from the full set and your models are maybe doing some feature selection internally anyway or some regularization, so they might be able to somehow deal with the large amount of features anyway, or roughly quite well, you might be ending up with a model that's a bit better in terms of predictive performance. So usually that's a trade-off. The other thing that I like, I guess, which I like about both, but which I like maybe a little bit more about forward search, is that you can actually somehow nicely interpret what happens here on this path, right? So you can say, well, if I would just use one feature, that gives me predictive performance of X. If I now add in a second feature, and the second feature is this, then I get a predictive performance of this. And then the third one is that, and that improves performance again by this amount. I guess for me that's a little bit more intuitive than thinking about how much do I lose when I remove stuff. But yeah, nobody is saying you cannot run both of these algorithms like after each other and then compare the results. Okay. Are there some extensions? Of course. So first of all, we could eliminate or add multiple features at once to increase speed. There are things like beam search and so on. We could also just run stochastic versions of the forward or backward search where we might not evaluate all potential options, but just do it randomly. We might even combine these forward and backward search techniques with, for example, filter techniques. So maybe you have a pretty huge feature space, and then these wrapper techniques are going to be quite slow, because for every feature subset you might have to cross-validate your model. So maybe you want to do something like use a filter, rank the features by the filter, or just compute their scores, and then transform the score into a selection probability, and then you just look at some of the features stochastically, but you look at the ones with higher filter scores with a higher probability. Well, I guess that's enough in terms of extensions for these forward and backward search approaches. Well, you can also alternate forward and backward search. So sometimes that's known as stepwise model selection, ARC, or in the Kohavi paper, I think that was called floating forward and backward search. So you do for example, you do a couple of forward steps, and then you might allow yourself also backward step, because now it might actually be possible to remove one of the features that you greedily have added in before. Maybe that becomes possible after a couple of forward steps, and then you can kind of make the set even smaller again. If you want to, you can also become a bit more black boxy in terms of optimization and a bit more, generic. You could run an evolutionary strategy on this. So evolutionary algorithms are nice techniques for these discrete black box optimization problems that we could have here. So we would, again, represent our search space as we did before as a vector of bits. And then we can run something which is called the mu plus lambda algorithm on this. So I don't want to spend now 30 minutes to explain evolutionary algorithms, so I guess I might try to do it in 2, and we'll link you to further material. If you don't know too much about genetic algorithms or evolutionary things, what do I mean with mu plus lambda? So what I mean is that the evolutionary algorithm is going to be, or some people call it also genetic algorithm, if we are working on bit strings as we are working on here. So we'll have a population, right? We'll have a population of candidates, and our candidates are just like our bit strings. Okay, at least I might write them down properly. So we have a couple of these guys here. So I'm not sure how much sense it makes if I'm just using 4 features, because there won't be too many choices. But I have a population of these guys. So in this case, it might be mu might equal 3. So my population is of size 3. Now, what does the lambda refer to? The lambda means I'm now going to create lambda offspring from this population of mu guys. And offspring means I will usually select 2 guys from the current population of size mu, and I will have them, mate. I will combine them, and this combination operation is usually called a crossover. And in this case, what we would usually do is some what is called a uniform crossover. So we would just pick. So for each bit, we would say we would pick the bit from one of the parents, like with a 50-50 coin flip random chance, right? So if I would combine this guy with this guy for the first feature, I would like flip a coin whether I take the 0 from this parent or whether I take the 1 from this parent, right? If they would be the same, well, I don't really have a choice. I would just copy over the bit. So that's crossover. And then the next operation we do is mutation. So after crossover, after we've like created the child from the crossover operation, we mutate that a bit, and mutate usually means we flip bits with a low probability. So for each bit, we kind of flip a coin, kind of an unfair coin, which is less likely to produce a flip, and yeah, some of these bits we would mutate. And we could even do this in a kind of biased or skewed manner, where we would say we would rather flip a bit from 1 to 0 than from 0 to 1, because if we go from 0 to 1, we make the feature set sparser. So that would be the mutation. Now, and we would cross over and mutate as many times as we need to create lambda offspring. And now we have the mu plus lambda elements, and we evaluate the offspring. And from the mu plus lambda options, so from our previous population and our current lambda offspring, we just boil it down to the best mu elements. And so kind of the best elements from the mu plus lambda survive. This is also why some people call this an elitist procedure. And then we have boiled it down to mu elements again, and then we iterate and do the same thing again and again and again and again and again, usually until some budget is depleted or we have reached some pre-specified value of performance, or performance doesn't progress enough anymore. So pick any of these criteria or mix them. And this is also visualized here. So here we have our chromosome. Yeah, so our chromosome is, yeah, kind of, or we have an encoding here. So you have our genetic encoding, and then for feature selection, that will be pretty simple. So like I said, it's just these bit strings here. And now we do the crossover, as I've explained. Then we do the mutation, as I've explained. Then we evaluate, and then we boil down to the mu elements. And yeah, I guess there's also usually a component in there, how you select the parents. You can just do that with uniform probability, or you can also put the parents in a certain sense on a roulette wheel and select them based on their performance, based on the performance we usually call fitness. Anyway, so guess you need more than, I would say, rather 2 hours or 20 hours to properly understand evolutionary algorithms. I now try to do this in, like, I guess rather, I don't know, more 5 minutes than 2. I'll stop this here. Genetic algorithms have been explored also somehow successfully for feature selection. Might be a good choice because I mean, they will usually take even a bit more time than these forward and backward searches, but these forwards and backward searches can also get stuck in local minima. Downsides of GAs are, well, they are more like a meta heuristic, so you can actually configure them quite differently, and that might be a challenge. If you haven't worked with them very often, then I guess you have to read a couple of papers or pick a specific software where people have like already configured and kind of pre-constructed well-performing GAs for feature selection. Another downside is that, like I said, they might be a bit more expensive, and they could also kind of meta overfit if you have them run for a too large amount of iterations and time. Here's an example where I guess I now really use BIC for a linear model. We can see what happens here. So here on the x-axis we have the number of iterations, and here on the y-axis you can see the distribution of the BIC value for the current population. So I have my population of mu guys, and here I plot their distribution of BIC values in a box plot, and what you can see is that the average fitness, well, I'm not sure whether let's say quote-unquote fitness goes down, because BIC, if it goes down, right, that's actually better. So my performance on average improves over time, over iterations, and that's exactly what I want. Well, actually, well, that's something that I might expect, and that's good, but in a certain sense, I do not even care too much about the average performance. So I would expect that goes down, but I'm also quite happy with the best performance of the best element in the population if that really goes down. But in this example here, both things are actually happening simultaneously. I've also here visualized in this lower plot the bit representation of the selected features. I'm not sure how informative that is, so at least that gives you maybe a little feeling for what happens inside of the algorithm and what this converges to. So I guess we might be seeing a couple of, I don't know, stable patterns for some of the features that are included in many iterations. Okay, let's wrap this up. So what is good about wrapper techniques? They can be combined with any learning algorithm. They can be combined with any performance measure. They kind of optimize the desired criterion directly. Disadvantage, evaluating the target function, the objective, is quite expensive, doesn't really scale too well if we have a large amount of features. Doesn't really use any additional info about model structure. With that I mean, so if we are like running a machine learning model on our data, I mean that kind of model learns something about the relationship of features with the target and which features are important. So that's usually not like fed back into the algorithm. Modern versions of wrapper techniques might do that, but the naive versions don't. And this is something that we didn't here discuss at length, but I want to spend now at least a few seconds on this now. Hopefully it is very, very obvious to you that we need to include all of these things in nested resampling. So I discussed that at length in the lectures on tuning. In a certain sense, we are doing here exactly the same. Yeah, so we're just like optimizing a different aspect of the model. So in tuning, we optimize different hyperparameter settings. Here we are optimizing which features to include, and we might do this on a validation set, might do this on cross-validation. If you do not embed these things into nested resampling, you will get exactly the same problems in terms of biasing your performance values. So yeah, be careful here, do this correctly, embed this into nested resampling. If you do not exactly understand what I'm talking about here, go back to the chapter on tuning and go back to the chapter on nested resampling. Everything that we are discussing there is basically directly transferable to this. And again, you can easily create examples where you overfit through feature selection on the cross-validation, and then your results might be severely biased. I guess that's a good point to stop here. Yeah, bye-bye.